Okay, so as you prepare for this test tomorrow, so first off, one of the things I'm going to let you do, I'm going to give you a half sheet of paper. Whatever you can write on one side.
One side.
One side. Anything. Whatever you can write on one side, you can use on the test. But again, listen to me. What?
Could we get like the exact same size paper and type it up?
No.
You can type it and then like glue it on there. Right?
No, it has to be handwritten.
Why not type? I can't read my hand.
What is that stuff? What's the difference between
I'm being nice. Do you really want to irritate me to the point that I'm just going to say, screw it, and you won't get it at all?
I take that.
Whatever you can write on one side. But again, don't get into when you cram so much stuff on it that then you can't find stuff. Okay? So basically, there's going to be two big sections to the graph. Okay? No, three big sections. There's going to be the thermodynamic section, which is brought to you by this equation. Q equals M delta T C sub P. That's basically the basis of the first one. The second one is going to be the gas law equation. PV equals nRT. And then the third part is going to be molarity. Okay? So those are going to be basically the three sections of the test. So if you want to divide your paper up into that, that's it. So let's start with this. What's M?
Molarity.
mass? You didn't know either.
Molarity.
I thought it was talking about the big M.
No, I pointed to this.
Well, I wasn't really paying attention, but when I saw M and I'm like, okay.
Oh, tomorrow's going to be your long.
You're telling me. You're not the one taking the test.
Okay, so let's hopefully this answer gets better. What units is mass measured in? Okay, all right, hope springs eternal. Okay, delta T.
Change in temperature.
Change in temperature.
Yeah.
Now, temperature can either be measured in Celsius or Kelvin, because it doesn't make any difference, and here's the reason why. If you're at 20 degrees Celsius, how many Kelvin is that?
293.
293, right? Add 273, so that's 293 Kelvin. If you're at 21 degrees Celsius, that's 294 Kelvin. So if the temperature changes by 1 degree Celsius, it also changes by
1 degree Kelvin.
1 degree Kelvin, okay? Because it's just an addition thing. So because it's changing temperature, it doesn't make any difference whether you work in Kelvin or you work in Celsius. It's going to be the same amount. This is why if physicists ruled the world, which we don't, thank God, but all the temperatures would be measured in Kelvin, because then you don't have to worry about zeros and negative numbers and all of that. Everything's a positive number, boom, here you go. But people would flip out and say, what's the temperature of the room? 293. Oh my God. Okay, it's 293 Kelvin. So C sub P stands for?
Specific heat.
Beautiful.
Yeah.
Great job.
Okay? Specific heat. What are the units for specific heat? What's one of them? Heather, what's one of the units involved in specific heat?
I guess it has to do something with temperature.
It does? That's down here. Well, let's back up. What does the Q represent?
Joules.
Joules. That's your thermal energy, right? So this has to be in joules. So play the game. I want to end up in joules. This is in
Grams.
This is in Celsius. So I got to get rid of those and end up in joules. So the units of specific heat then have to be what? Joules per gram degree Celsius. Or you can also see it as joules per Kelvin. It's the same thing. Okay?
You don't put the degree mark for Kelvin, right?
Oh, it's some debate. Typically you don't. It's just Kelvin. Boom. So it's the same thing. So here, and again, I beg of you, pay attention to the units when you're doing this stuff. Just literally, some of you just write down random numbers. There's no point in it. This is an organized thought process, okay? And numbers that don't have any units have no meaning. Literally, there's no meaning to them. They don't mean anything to you. They don't mean anything to me. No, bad, okay? Keep things organized. So here's why this works. Because if I have joules per gram degrees Celsius, and that's what I'll have it as on the test, is degrees Celsius. So then when I multiply it together, the grams cancel out, the Celsius cancels out, you're left with joules. Joules. Okay. Anybody happen to remember the specific heat of water?
4.18.
4.18. Beautiful. 4.18 joules per gram degrees Celsius, which is comparatively a large value. So here's how this is going to play out. I'm going to tell you exactly how this problem is going to work. I'm going to say, okay, hey, you have a certain mass of water. I want to heat it from 20 degrees to 25 degrees. How much energy is involved? Plug and chug technique. That's going to be the easy version. Or I'm going to say a certain amount of energy is needed to take 5 grams of a substance and raise it 5 degrees Celsius. What's the specific heat? That's going to be a little bit more complicated just because of the fact that you're going to have to solve for specific heat, or you're going to have to solve for temperature or whatever. So, but again, pay attention to the units. So here's the other thing that you're going to have to be able to look at. I would say, okay, I'm going to have 10 grams of water. Okay? So if I'm going to keep the mass constant, and I want to raise the temperature more and more and more, what's the relationship between energy and change in temperature? Is it a direct relationship, or is it an inverse relationship? Direct. Why?
Because it's change the temperature goes up, energy goes up.
What?
The amount of energy goes up.
Yeah, I thought you said NV. It's like NV. Okay, yeah, the amount of energy goes up. So if I keep mass constant, the more I want to raise the temperature, the more energy it's going to take, right? Which makes sense. Hey, you put it on a hot plate. If I only want 1 degree Celsius change, hey, that's not much energy. If I want to make it boil, hey, that's going to take a lot more energy. Okay? So something like that. Now, promise you, I'm going to ask you a graph where you have something like this is temperature and this is energy that we're dumping into it. Okay? So what happens on any horizontal line? Are you building potential energy, or are you building kinetic energy?
Well, it's potential energy that's going to turn into kinetic energy.
Okay, but if it's just a horizontal line,
Potential.
that's right? This is you're dumping energy into the system, but you're not changing the temperature. So this happens when you have like a phase change. So like, let's say for example, when you melt ice, okay? If I gave you a chunk of ice and said, hey, melt it. All right, well, you got to dump energy into it. So let's look at this. Here's a chunk of ice, right? You want to melt it. In the melting, are you going to break bonds, or are you going to form bonds to melt ice? Break bonds. So which direction does energy flow? In, right? I've got to dump energy into this system to break the bonds that hold it together as ice. So I'm going to dump all of this energy in, but it's not going to change the temperature, because all of that energy is going to break the bonds. That's why this would be a horizontal line. Now, as soon as it all melts and it's liquid, then if I continue to heat it, then what's going to happen to the temperature? Then the temperature is going to go up, because now that energy is increasing the kinetic energy of the particles. So when you have a sloping line on this graph, that means I'm continuing to dump energy in, but now these particles are taking it and moving faster. So let's say it plateaus again. Okay, so let's say this is water. Here was ice. Okay, at this point I'm at 0 degrees Celsius. I warm it up to 100 degrees Celsius. So what's happening on that second horizontal line? So now I'm making it, I'm boiling. So am I continuing to dump energy in? Yes, but now it's being stored, right, to break the bonds that hold the water molecules together. So here's a water molecule, and then here's another one, okay? The bond that holds the water molecules together, is that an intermolecular bond or an intramolecular bond? Inter or intra? Inter. It's like an interstate. It's between the two parts. So when you boil water, you're not separating it into hydrogen and oxygen. You're just giving these individual water molecules so much energy that they turn into vapor. They're able to free themselves. Boom. So it's kind of like second graders that are held together, right? I want to give them so much energy that they actually begin to float off, which would be kind of cool. So, but you've got to give them so much energy to break the bonds that hold them to each other, or once you give them that much energy, then you get like little second grader vapor pockets floating around, which would be really weird. Wow, it's raining second graders. Cool. Okay. So, now, if I want to break the bonds that hold the hydrogen and oxygen together, is that intra or inter? Intra. This takes a lot more energy. Okay? These bonds are a lot stronger. That's why when you boil water, you always break the easiest bonds first. It's kind of like the old adage, a chain is only as strong as its weakest link. When you dump energy into a system, you always break the weakest bonds first. Okay? So this is why when you boil water, you're not getting pockets of hydrogen and oxygen. It's just pockets of extremely high energy water molecules themselves. Okay, so true or false? I can put energy into a system and not change the temperature. True. Okay? But could I dump energy in and change the temperature? Yeah. Now, if I gave you a task, I said, here's your task. I want you to make ice. Okay? That's your task. Muffin, I'm going to give you my cup of coffee, and I'm going to tell you I want you to make it into iced coffee. What would you have to do? Dump energy in or take energy out? Take energy out. Are you going to form bonds or break bonds? You're going to form bonds. So anytime bonds are formed, you're releasing energy. Now, let's look at what happened in the magnesium oxide lab that you just gave back. Okay? So, if you look at what happened there, you had magnesium, and you reacted it with oxygen. Now, some of you on the empirical formula, you found that mole ratio, and it was like 1 to 1.2. You really can't round this. So this is what I did on your papers. If it's like 1.2, that's too far away on a mole ratio to say, oh, it's MgO. So this is what I kind of tried to show you. If it was 1.1, okay, yeah, we could round it. But a lot of you got like 1.2 or 1.25 or even 1.3 on that mole ratio. That's too far away to call it a 1-to-1 ratio. So this is what I was showing you, is that if it's 1.2, that's like 1 and a fifth, because 1 divided by 5 is 0.2. So this becomes like 6/5. So on that empirical formula, on that lab that I gave back, so if it was 1.2 or 1.3, this is what I showed you that you had to do. You just can't say, well, it's a 1-to-1 ratio. No, it's not. It's a 1 to 1.2 ratio. And that's not close enough to round to and just call it NGO. Okay, but theoretically, here's what we should get. Is MGO to balance it. This is what we're going to get into next week. Okay, these are what we call coefficients. These are what you use to balance the equations. So I got 2 magnesiums, I got 2 magnesiums, I got 2 oxygens, I got 2 oxygens. Hey, we're cool. No worries. So when you look at this, if you look at what has to happen, the oxygen has to split apart. So you do have to break one bond to get this oxygen apart so that it can individually bond with the magnesium. But here's the deal. When you all did this, when you burned that magnesium oxide, do you think, even though we had to heat it but to get it started, but once it started, it was giving off all of this energy, it was giving off all of this light. So if you look on an energy versus reaction, okay? So you started here with the magnesium and the oxygen, right? So those are my separate things that I had. So what do you call this first hill with the roller coaster? That energy that we had to dump into it. Activation energy, okay? So this is my activation energy. That's why I had to heat it up to start it. So, but once I got it started, then I ended up way down here, okay? So here's my products of magnesium oxide. This is why so much energy was given off, because of the fact that we released so much energy from where we started to where we ended up. So this hill, activation energy. I promise you, you've got to be able to draw a diagram like this. Okay? Boom. There's my activation energy. Here's where I start. Here's where I end up. As long as this is down here, we end up giving off energy because of the fact that we formed a whole bunch of new bonds. Your gasoline engine in your car works because of this. You have octane, which is in your gasoline, and you have oxygen that's in the air. It combusts within your engine. You get carbon dioxide and water vapor. In the process, it gives off thermal energy, which is why when it gets cold outside, this is why you turn your heater on in your car. So your heater is basically taking that thermal energy from the process, heating up the air. You can stay nice and toasty inside your car. So, now, what if I gave you magnesium oxide, and I said, okay, hey, I'm going to be a jerk. I'm going to give you magnesium oxide, but I want you to break it apart into magnesium and oxygen. What would you have to do? Put energy in or take energy out? You're starting here. Yeah, I got to push this roller coaster all the way up this hill. So now I've got to break the bonds that hold the magnesium and oxygen together. So now that would take a tremendous amount of energy dumped in. So if I give off energy in the forward direction, if I reverse this thing, I've got to dump a lot of energy into it. Okay? So I promise you there's going to be questions on this. Think about, remember the hot pack lab? Okay? Right? Now, you have back all the labs that you have done. Any lab is fair game. So what did you do with that little hot pack lab? What's the first thing that you did to start that?
Snap that thing.
You snapped the little metal thing. That represented the activation energy. Energy was given off, right? It got really, really hot. So this thing rolled downhill. So then, when we wanted to get it back to its initial state, what did we do?
Boil it.
We boiled it because we had to push it back up the hill to break the bonds. Okay? So this is one of the key things I'm going to expect you to know. Promise you, promise you, promise you, promise you. Okay? All right. Gas law. PV equals nRT. Okay? So let's talk PV equals nRT. P stands for pressure. Measured in. There's a whole bunch of things, but we're going to keep it in atmospheres. Okay. So right now you all are under about 1 atmosphere of pressure. Okay. You're used to it. It's 1 atmosphere of pressure. Okay. V measured in liters. Okay. So don't make this difficult. When I multiply pressure times volume, what do I get? I get atmosphere liters. Okay? Okay, got that side. Then I've got N. N is going to be moles. This is your moles. Okay? Moles. R, ideal gas law constant, which is in liter atmospheres per Kelvin. And then you have the temperature in Kelvin. So what units do I get out of this side of the equation? Yeah, both sides have to produce atmosphere liters. I can't have this side producing grams and this side producing liters because grams aren't equal to liters. So both sides have to be the same. So this is going to be just, hey, if I keep this side of this equation same, in other words, if I keep the temperature the same, so let's say, for example, sounds odd, I happen to have a syringe in my desk drawer. So here's the syringe, okay? So I take this syringe, and I push down on it, right? So what should happen to the pressure inside? Why? To produce the same, the same inert, okay? So as long as I keep inert the same, if I keep this and push it down, so I'm making the volume get, pressure has to increase. Now, if I reverse it and pull it out, the pressure should decrease because I'm increasing the volume, okay? Now, what if I lock this in place, okay, where it can't move, can't change the volume, and I drop it into boiling water? What should happen to the pressure inside? What'd you say, Moses?
Increase.
Why?
Because you're pumping energy into it.
So,
You're making the pump move faster.
okay, remember, pressure, when you look at pressure, pressure is force per unit of area. So, we measure it in atmospheres, but it's force per unit of area. So, when I warm this up, the particles inside are going, ah! Okay, I have a lot more energy. So they're going to start flipping out, so they're going to start hitting the sensor with more and more energy. So it's like giving second graders bagfuls of M&Ms. They're going to flip out. If you're the teacher, your leg is going to be hit a lot more often by these little ankle biters because they have a lot more energy. Okay. So as temperature goes up, pressure should go up. Now, what if temperature goes up and I want to keep the pressure the same? What would have to happen to the volume? It would have to increase. Okay? So if I don't lock it in place and I heat it up, this would get bigger, the syringe would get bigger, it would push out to create a bigger volume to keep the same pressure. So that's just a function of, hey, keeping track of what you've got. So the last one is molarity problems. Here's your molarity. Stands for molarity, right? Okay? Okay? And molarity is measured in what units? Did you say moles per gram?
Here. I didn't say gram.
Okay, I thought somebody said moles. I was going to flip out. Moles per liter. There's 3 calculations you have to be able to do with this. What's one of them?
Finding
Find the molarity. Okay? Find the molarity. I'm going to give Moses this beaker, and it's going to have 500 milliliters of water in it, and I'm going to give him 200 grams of potassium permanganate. He's going to dump it in there. Hey, what's the molarity? Okay? Promise you. You've got to be able to do that without thinking. What's the second type of problem you're going to have to be able to do?
5 grams.
Well, describe the preparation. Okay? So how would you prepare something? So, and this is the most realistic application. So, you know, you look at all the labs that you all have done. Okay? 1 molar hydrochloric acid, 0.5 molar magnesium nitrate, all of these things. So as a chemistry teacher, one of the most important things that I've got to be able to do is prepare the solutions. So if I type up a lab and I say, hey, these kids are going to need 2 molar hydrochloric acid. Well, if I can't mix up a solution of 2 molar hydrochloric acid, then you all can't do the lab. So this is going to be one of the most important things that you have to be able to do. Okay? And again, your answer to this is going to be in this format. You're going to say, dissolve so many grams of something in enough water to get 500 or whatever the volume is of a certain molarity. This is how I'm going to want this question answered. Now, what's the third thing that you've got to be able to do? This is the third one's the simplest one. Just find the number of moles in a solution. So if I say, hey, here's 50 milliliters of a 0.5 molar solution, how many moles of copper nitrate are in there? So this is the easy one. On that third step, you only have to do is take the volume in liters and multiply that by the molarity, which is moles per liter. Liters cancel out, you get moles. This is the easiest one. Okay? This is the easiest one by far. Okay, so here's what you're going to get for the test. This half sheet of paper, one side. Okay? One side. okay? You only get the side, you don't get the kick side, okay? You only get the side, no kick. Whatever you want to write on it, it's up to you. But again, and I've seen this happen more than once, don't write so much stuff and write so small that you can't find it, okay? Now, if I were you all, here's the other thing that you've got to be able to do on this whole mole calculation in empirical and molecular formula. I maybe write down the definition of empirical and molecular formulas, okay? If you don't know what it is, you have a textbook, you can Google it, whatever, okay? But you've got to be able to find empirical formulas and molecular formulas, okay? That is one of those, promise you, you've got to be able to do that without thinking, okay? You got to be able to do empirical formulas and molecular formulas. Percentages, mass, whatever, okay? Now, here's what I promise you is going to happen on the test. You're going to have a situation where I'm going to say, okay, and it's going to be real data. I'm going to say, here's this empty crucible. It has a mass of 30 grams. That's the empty mass. And then I'm going to tell you, I'm going to put some iron or whatever it is in it, and then the mass goes up to 31.50 grams. What's the mass of the iron in the crucible? Yeah, don't make it difficult. You subtract it out, boom, there you go. Then we're going to heat it up, okay? And it's going to react with chlorine or oxygen. I will tell you what the gas is that it's going to react with. And then I'm going to say, okay, then we weigh it again, and the mass becomes 32.50 grams, okay? So what mass of gas did I add? Yeah, so any additional mass comes from the addition of the gas from the flask. Yes?
Would you want us to put 1.000 for the force?
No. Look, when you subtract, this scale only measures to here. So when you're adding or subtracting, remember, it's the least precise place value. Because here's the deal. If you tell me that the mass is this with 4 significant digits, I think that you had a different scale than what you measure here. So if you're subtracting, you can only write this as 1.00 grams. That's it. I can't put 1.000 because then it looks like I used a completely different scale. Okay? Now, when I multiply, if I multiply by this something, then I could have 3 or 4 significant digits. But when I'm just doing this subtraction, this is what I've got. Okay? So what would be the total mass of the substance in the crucible? 2.5. Okay? So this is the kind of data that you've got to go off of. So you've got to be able to do empirical and molecular formulas either based upon real lab data or just off of percentages. Okay? You've got to be able to work off both. And remember, your empirical molar mass times some value of N is going to equal your molecular molar mass. And this N will always be a whole number. If you find this N and you get like 2.5, bad. Okay, so here's what you're going to get. So this is not due because I'm giving you all of the answers. So this is just basically a series of these mole calculations. Grams, you've got how do you prepare the solutions, empirical formulas, percentages into molecular compounds. There's some density stuff on here, okay? Don't think that density might rear its ugly head. So all of these are worked out. Now, the reason that there's points assigned to this is because at one point I actually gave this as an assignment, but I've shifted it just as the review. Okay, so here's the solution to all of these problems. Now, some of these are marked out because I didn't feel like rewriting the whole thing, and it dealt with hydrates. We didn't have time to do hydrates. So you're going to see some of these just scribbled out. Just don't worry about it. Then that's kind of all the mole calculation stuff, and then you're going to have this one. This is more of the thermodynamics, specific heat and gas law stuff. Okay, and then you're also going to get the answer key to it. So you're going to get 5 pieces of paper. The blue sheet of paper, it's going to have what you can write on it. All of of these problems, and then the stapled sheet is the answers to all of these problems. Then you're going to have this page and then the answer to it. Especially on this one, don't look at my answer sheet and go, oh yeah, Burkamp, yeah, that's how I would have answered that. Yeah, cool. You're on a roll. No, okay, don't do that. Okay, John, shut that down. I am done.